Okay, so this is lesson 2.5. It's all about the properties of the different functional groups. What's important today is that we're going to learn how to use the intermolecular forces in order to predict the physical properties of organic compounds that have different functional groups in them. So, early in the unit, and in the last unit, we spent a lot of time talking about intermolecular forces. What are the different kinds of intermolecular forces again? Paige? Good. So dipole, dipole, and London dispersion. Those are the two big categories. Van der Waals also often used synonymously with London dispersion. So that's the same thing. So the dipole dipole happens when you've got differences in electronegativity between the atoms in your molecule, and you end up with an asymmetrical molecule so that one side is a little bit negative and the other side is a little bit positive. So dipole dipole happens because you've got one chunk that's a little bit negative, one chunk that's a little bit positive. The negative chunk on one molecule will be attracted to the positive chunk on another molecule, holding those molecules a little bit tighter together than they would be if those forces didn't exist. On the other hand, if you have London dispersion forces, that means the electrons on one molecule are attracted to the protons in the nucleus of the other molecule. Those forces are a lot weaker than dipole-dipole forces, but they still exist in every molecule. Then hydrogen bonding is a super strong version of dipole-dipole forces. When do we end up with hydrogen bonding? Yep, nitrogen, oxygen, and fluorine. Those small atoms that have lone pairs. If you have nitrogen bonded to a hydrogen, if you have oxygen bonded to a hydrogen, if you have fluorine bonded to a hydrogen, you'll end up with hydrogen bonding, which is really a misnomer. It should be hydrogen intermolecular forces, not a real bond, just a force between molecules. Okay, so there's a recap of intermolecular forces. And it turns out that these intermolecular forces are really important for giving different functional groups different properties. Compounds that have the same functional group will end up with similar properties because they have similar intermolecular forces. The functional groups are really what determine if a compound can form hydrogen bonds or if they have dipole-dipole forces. So they're really important for determining our intermolecular forces. Okay, so let's start with alcohols as our example. Remember that there can be three different kinds of alcohols. The primary alcohols have the OH that's attached to a carbon that's only attached to one other carbon. The secondary have the OH attached to a carbon that's attached to two other carbons. And the tertiary has the OH that's attached to a carbon that's attached to three other carbons. So that's primary versus secondary versus tertiary. But take a look at these four different kinds of alcohols and think about this for a second. Which ones have the highest intermolecular forces and therefore would have the highest boiling point? Okay, so when we look at all four of these molecules, they all have bonds between carbon and hydrogen. Is that bond ever polar? No. The electronegativity difference is too small. Carbon has an electronegativity value of 2.5. Hydrogen has an electronegativity value of 2.1. The difference is only 0.4. So anytime you just have bonds between carbon and hydrogen, the molecule will be nonpolar. But in all of these molecules, we also have OH groups. They're all alcohols. So there's always a bond between carbon and hydrogen, and between oxygen and hydrogen, and always a bond between carbon and oxygen. What's the electronegativity value for oxygen? 3.5. Yep. Hydrogen, 2.1. So anytime I've got a bond between oxygen and hydrogen, that bond is going to be polar. Then for carbon and oxygen is again 3.5, carbon is 2.5. So that bond is also polar. So all of these molecules have polar bonds. They're all going to end up, because for every one of them, if I draw it with some geometry, my carbon is bonded to an oxygen that's bonded to a hydrogen. The oxygen end will be a little bit negative. Doesn't matter what's on the carbon end, but this side over here will be a little bit positive. So all these alcohols are going to be polar. So they'll all have dipole-dipole forces between them. But which one is going to have the most dipole-dipole forces? Anthony? Okay, so that's a possibility when we look at that. Any other options? Yeah, the last one has two polar groups on it. The fact it has two polar groups is going to outweigh the non-polar portion. So that's what's going on here. That last one is going to be the most polar. It has the highest intermolecular forces, and it'll have the highest boiling point. And really, it's this polarity, this chunk of the molecule, that determines a lot of the physical properties of all alcohols. Okay, so when we look at the physical properties of alcohols in general, they've got this OH group, and that OH group is really, really polar.
Sorry, just a question about the previous, the molecule that had.
So when we're looking at these alcohols, the OH group is super polar. But as the number of carbons in that compound increases, that their non-polar nature will outweigh the polar nature of the OH bond. So for example, where did my pen go? If I've got a molecule like this, it's got one little polar portion. But if I've got a really, really big molecule, it's got a much larger non-polar portion. And that non-polar portion starts to outweigh the effects of the polar portion. As a result, a molecule like the second one will be a lot less soluble in water. A molecule like the first one is more soluble in water. And all that solubility in water, all that dissolving in water, happens because the molecules of the alcohol are just as attracted to the molecules of water as they are to themselves. the molecules of the alcohol are just as attracted to the molecules of water as they are to themselves. I'll draw some diagrams on the next page to kind of show you what I mean. But that's because of the ability to hydrogen bond. The oxygen lone pairs are going to be super attracted to the partially positive hydrogens in water, as well as the partially positive hydrogens in other alcohols. And then this polarity also affects the melting and boiling points. It means that they've got really, really strong intermolecular forces. So as a result, they have a higher melting point and a higher boiling point than an alkane that has the same number of carbons. Most alcohols are liquids at room temperature, whereas an alkane of the same size, like methane versus methanol, methane is a gas at room temperature, methanol is a liquid at room temperature. Also, they're all super flammable and most of them are poisonous, even ethanol when you drink too much of it. Okay, so let's talk about this hydrogen bonding and the attraction for these molecules for themselves and for water. So there's a molecule of ethanol. When I look at a molecule like this, I know that the oxygen is pulling electrons away from the carbon and the hydrogen, and it's a little bit negative up here. The hydrogen as well as the carbon are going to be a little bit positive. That means that one molecule of methanol is going to be really attracted to another molecule of methanol. This partially positive hydrogen right here, it's losing electrons to its own oxygen, so it's got a partial positive charge. Because it's got that partial positive charge, it's going to be very attracted to the negative charge on an adjacent oxygen. That attraction is the hydrogen intermolecular force, or the hydrogen bond, right? So this force is pretty strong. It holds those molecules together pretty tightly. And this wouldn't dissolve in another solvent if the molecules weren't also attracted to the molecules in another solvent. So if I'm trying to dissolve something like methanol in water, well, I have to decide, is that actually going to be soluble in water? I'm going to draw my water molecules in purple. And my partial charges again in orange. So once again, a water molecule has a negative end and a positive end. So because this hydrogen on a water molecule is a little bit positive, it'll also be attracted to the oxygen in a methanol molecule. So alcohols can form hydrogen bonds with themselves, and they can form hydrogen bonds with water. They're just as attracted to the water molecule as they are to themselves. And as a result, they're soluble in water. They'll dissolve in water. The water molecules can get in there and surround the methanol molecules. As a molecule of alcohol gets bigger and bigger and bigger, it's harder for the water to do that because they've got a larger nonpolar part. Yeah, no, go for it. So for ethers, I'm going to take a second and draw an ether. I'm going to do a terrible job drawing an ether. Okay, so ethers have a bond between carbon and oxygen in the center of kind of two carbons there. Is the bond between carbon and oxygen polar? Yeah. So oxygen is going to be pulling electrons away from the carbon, and that oxygen is going to end up a little bit negative. So is this molecule polar? Yeah. So this is a polar molecule. It's got oxygen in the center, but does it have hydrogen bonding with itself? Brooke, why not?
Because it's like CH bonding with O, not just H and O.
Exactly. Because it doesn't have oxygen bonded to a hydrogen. So it can't have hydrogen bonding to itself. As a result, they're polar, but they're not as polar as alcohols, and they don't have hydrogen bonding. However, they can do hydrogen bonding with water. I'm going to draw on the board here. Okay, so again, because of that polarity, they're usually soluble in water, but the solubility decreases as the size of the molecule increases. There's just a bigger non-polar chunk. It's harder for water to get in there and surround the ether molecules. And for melting and boiling points, they're lower than alcohols that have the same number of carbon atoms, but higher than alkanes. So if I needed to rank something like this one, which is dimethyl ether, so that's got 2 carbons. If I'd compare that to ethanol, and to ethane, these 3 molecules all have the same number of carbons. They each have 2 carbons, but ethanol has hydrogen bonding, and it's superpolar, obviously. So that would have the highest boiling point. Then dimethyl ether, that's polar, but it doesn't have hydrogen bonding. So it would have the second highest boiling point. And then ethane is completely non-polar. That would have the lowest boiling point of the 3. They're also super flammable, just like alcohols. Amines. Take a second, draw methylamine, methanamine, and think about it. Is it polar or non-polar? And does it have hydrogen bonding? So that's methanamine with all the carbons and hydrogens and geometry shown. That molecule has some bonds between carbon and hydrogen. We know those aren't polar. What about the bond between carbon and nitrogen? Polar or not? Well, nitrogen is 3.0, carbon is 2.5. So the bond between carbon and nitrogen is just slightly polar. But then I've also got this bond between hydrogen and nitrogen. Nitrogen 3.0, hydrogen 2.1. So that bond, the electronegativity difference is 0.9. That bond is slightly polar. Well, it is polar. So polar bonds between carbon and nitrogen and between nitrogen and hydrogen. That means that the nitrogen is pulling electrons away from carbon and away from two hydrogens. That means that the nitrogen is a little bit negative. The hydrogens are a little bit positive, so is that carbon. Is that molecule polar? Yeah. So this molecule is polar. If I had a second one of these molecules drawn, would there be hydrogen bonds between those molecules? Well, think this through. I'm going to draw another one. So if I draw another one, again, the nitrogen is a little bit negative. The hydrogens are a little bit positive. Are these hydrogens that are a little bit positive attracted to the negatively charged nitrogen? Yeah. So is there a hydrogen bond there? Yeah. So amines, here we see can be very polar and can have hydrogen bonding. But what kind of amine is this? Is this primary, secondary, or tertiary? Yeah, this is a primary amine. We know that because the nitrogen is only attached to one carbon. I'm going to draw as well a tertiary amine. Here, I've got the nitrogen attached to 3 methyl groups. So this is trimethylamine. This is slightly different though. Now, you've just got bonds between carbon and nitrogen. Those bonds are all polar, but they're not as polar as the bonds between hydrogen and nitrogen. So out of those 2 compounds, well, first off, does the second one have any hydrogen bonding? The tertiary amine? With itself? No. It would with water, but not with itself. So this one doesn't have any hydrogen bonding with itself. As a result, this one is going to be less soluble in water than this one. This one's just polar. The first one has dipole-dipole forces and hydrogen bonding. The second one just has dipole-dipole forces. So when we're considering the properties of amines, we need to consider if they're primary, secondary, or tertiary. So these amines, carbon and nitrogen bonds, and the nitrogen and hydrogen bonds are polar. So they're polar. They have hydrogen bonding with water all the time and with themselves if they're primary. So then all of that, the solubility in water, they are going to be soluble in water. The small ones are so soluble, we say they're miscible. That means they can mix completely. But the solubility decreases as the number of carbon atoms increases. And that's because, again, they're going to have a larger non-polar chunk. Then for melting and boiling points, the boiling points of primary and secondary amines tend to be higher than those of tertiary amines. And that's because the primary and the secondary can form hydrogen bonds with themselves, and the ones that are tertiary can't. That's like we just drew in the last slide there. Also, they're widely found in nature. They're often toxic, and the small amines smell fishy. They also act as weak bases. So when you add a salt or add an acid to a weak base, it neutralizes it. So adding vinegar to an amine produces a salt. And that's why adding lemon juice or vinegar to your fish and chips can neutralize the fishy smell. Commonly used in cooking. These. Try and draw these and then rank them in terms of highest boiling point to lowest. Then justify your answer. Trimethylamine, methylamine, or methanediol. So here I've got trimethylamine, methylamine, and methanediol. Which ones are polar? Anthony? Is that it? Yeah, they're all polar. So they're all polar. So we have to then consider which ones might have hydrogen bonding. And that, the answer is the two on the right? Nitrogen bonded to hydrogen here, so it'll have hydrogen bonding. And here I've got oxygen bonded to hydrogen twice. So which one do you think is going to have the strongest of the intermolecular forces? Yeah. This one is going to have the strongest intermolecular forces, therefore the highest boiling point. The forces holding those molecules together are so strong it takes more energy to separate them. Second highest will be methylamine, and then trimethylamine. Okay, then rank the following in terms of highest solubility in water to lowest. Justify your answer. So methyl ethyl ether, ethanol, and 1 nonenol. Okay, so here I've got methyl ethyl ether, ethanol, and nonenol. So looking at this, all of them have an oxygen in them. The ethanol has an oxygen bonded to a hydrogen, as does the nonenol. So when we look at these three, we've got a bunch of things to consider here. First off, which one do you think would have the highest solubility in water? Why?
Because it's smaller and it can be hydrogen bonded.
So the ethanol will have hydrogen bonding with water. Ethanol molecules will be just as attracted to H2O as themselves. So the water molecules will get in there, surround the ethanol molecules, and that will dissolve very, very well in water. So that one's going to have the highest. Okay, then
Hydrates it faster because it's attracted to it. So in terms of like polarity and when there's high strong bonds, it usually is.
one's kind of the obvious choice here. So this one is the most soluble in water. Then I look at the other two molecules. I see that this one's polar. Will it form hydrogen bonds with itself? No. But would it form hydrogen bonds with water? Yeah. So I know that that oxygen in the center is a little bit negative. That would be attracted to the partially positive bits on a water molecule. So it would be soluble in water. Then I'm going to compare with this one. The nonenal has this chunk over here on the right-hand side that's very, give me just a sec, that's very polar. It's going to form hydrogen bonds with itself. So this part's polar. What about the second half of this molecule? Is this side of the molecule polar? That side's non-polar. So now this molecule has a very large non-polar portion and just a small polar portion. This molecule, it will form hydrogen bonds with water. It's pretty small. It's probably pretty easy for the water molecules to get in there and surround them. So I would say, I'm not entirely sure which one of these two would be more soluble in water. This one would form better hydrogen bonds with water, but it's so big, its non-polar part probably outweighs the polar part. If you were answering this on a question, on a test question, you'd need to point that out. This one, the top one here, and my slide changed, so that's not even the same thing. The methyl ethyl ether, it's a lot smaller. It's got a lot smaller non-polar portion, so it's probably more soluble in water. I don't know for sure, though, without looking up the data, but that would be my prediction. I want to also talk about the physical properties of aldehydes and ketones. So remember that the second half of all these functional groups all have a carbon double bonded to an oxygen. We know that that carbon double bonded to an oxygen is going to be polar. So all of these aldehydes and ketones and carboxylic acids and esters and amides are going to be polar. For aldehydes and ketones, there's no bond between oxygen and hydrogen, though. So there's not going to be any hydrogen bonding between the molecules, but same as with the ethers, there is going to be hydrogen bonding with water. And again, because they've got that one polar chunk, the small ones are going to be soluble in water, and they're going to be less soluble the bigger they get. And for melting and boiling points, like the ethers, they're going to be lower than the corresponding alcohols, but higher than the alkanes. Because again, they're less polar. So once again, this polarity changes everything. The small ones, you're familiar with. Things like formaldehyde, they tend to be really stinky and unpleasant, but as they get larger, they tend to smell nice. The smell of cinnamon is because of an aldehyde, which we call cinnamaldehyde. Ketones tend to smell sweet, and often they're really useful in chemical reactions because they've got a polar portion and a non-polar portion. Like acetone. What do you know acetone from? Nail polish remover, right? So acetone is a ketone, and it works as such a good solvent because it's got a polar portion and a non-polar portion that can dissolve non-polar chemicals. Then when we get into the carboxylic acids, remember that that's this functional group. Is this going to be polar? Yeah, it's going to be superpolar. We've got a bond between oxygen and hydrogen, a bond between carbon and oxygen, a bond between oxygen and carbon there. The whole carboxylic acid functional group is very polar. It also forms strong hydrogen bonds with itself and with water because you've got that oxygen bonded to the hydrogen. And again, because of all that, the small ones are very soluble in water. And then they're less soluble the bigger they get. Methanoic acid, ethanoic acid, propanoic acid, butanoic acid, they're all so soluble, we say they're miscible. But as they get large, they'll become less and less soluble. And then again, their melting and boiling points for the number of carbons they have are quite high because of that hydrogen bonding. So you're starting to see a trend here. It really is just looking at these functional groups, deciding are they polar or not, do they have hydrogen bonding or not, and that determines their physical properties. Except for the smelly bit, I'm not even, like, you're not going to test it on that. It's just interesting. Okay, then we've got the esters. So remember that esters are like this, except that they've got another carbon group over here. So esters are going to be polar, but do they have any oxygen directly bonded to a hydrogen? No. So they don't have hydrogen bonding with themselves. They will form hydrogen bonds with water. Again, the small ones are soluble in water. As they get bigger, they become less and less soluble. And then they, again, have higher melting points than alkanes, but lower than carboxylic acids or alcohols. And esters tend to smell great. They tend to taste great. They tend to smell great. The tastes and smells of fruits are often because of esters that are in them. That really characteristic smell of like raspberry or banana or peach or any of those things, most of that comes from the esters in the compounds. So later in the unit, next week, I think, we'll do a lab where we synthesize some esters and try and recreate some of these cool smells. There's one that smells like wintergreen gum that always works really, really well. And then some that smell like bananas and apricots and other things and are not quite as reliable, but sometimes you get lucky. So those are esters. And then lastly, we've got the amides. I guess I didn't need to erase all that. But remember, amides still have that carbon double bonded to the oxygen, but now that carbon is bonded to a nitrogen. So because of this, depending what's on the nitrogen, that could be a hydrogen, which would mean that the amide has some hydrogen bonding, or it could be CH3s or something like that. As a result, there wouldn't be any hydrogen bonding. So they're going to be polar, but they may or may not have hydrogen bonding. And all of this, again, is going to determine their solubility. They're soluble in water because they're polar, and as the non-polar portion increases, they become less soluble. The primary ones have higher melting points and boiling points than carboxylic acids, but the tertiary ones would be lower. Okay, take a minute, draw these, and try answering. Which of the following would have, well, rank the following in terms of boiling point from highest to lowest. I've got hexanal, hexanol, hexane, and dihexyl ether. Oh, minor typo. So not, actually kind of a major typo. This should be YL, not AL, so that helps. Okay, so now I've got all 4 molecules drawn here. That's just the first bell, right? Which one do we think is the most highest boiling point, has the strongest intermolecular forces? The hexanol. It's got oxygen bonded to hydrogen. It's going to have hydrogen bonding, and it's polar. This one also has a hydrogen here, so it will have some intermolecular or some polarity, but no hydrogen bonding with itself. This one, again, it's large. It's got some polar bonds. This one not polar. So it'll have the lowest boiling point.